So the next CPU architecture or CPU organization is called as general register CPUs, right? These are the types of CPUs that we typically use nowadays, right? These are typically used nowadays. And these are widely used. That's why they're called as general register CPUs. Again, here you notice that here there is a lot of focus on the registers. Again, registers are memory locations within the CPU that we have discussed about, right? So within general register CPUs, there are two broad ideas, right? Or two broad subcategories. One of them is called as register memory reference architecture. The other is called as register reference architecture. They're very similar except for a couple of key differences. In this video, we'll learn about register memory or register to memory. This is sometimes read as register to memory reference architecture. Once you understand register to memory reference architecture, you'll also be able to understand register reference architecture very easily. In a nutshell, in a register memory reference architecture, imagine I have some opcode, right? Suppose if I have something like multiply, right? Some ALU operation. Again, we are only discussing about your ALU operations here. In all these architectures that we've studied, we are focusing mostly on arithmetic and logical operations, right? So imagine I have a arithmetic operation like mul, which stands for multiply. Here my register memory reference architecture basically means that I will have one register here. I'll have a register, some register, R0, R1, R2, whatever register I have. This thing will be a memory location, something like 2080, right? So what I have here is my first opcode. Look at this. This is my opcode, my first operand. My first operand or operand 1 is always a register. My second operand is actually a memory location, right? My memory location is my second operand. This is what is called as register memory reference architecture. In register reference architecture, both of your operands will be in registers. For example, look at this. Mul R0, R1. Or instead of comma, we just say mul R0, R1. Here, if you notice, both the operands are in registers here, right? So register to memory reference architecture is used when you have fewer registers, right? So this type of architecture is used when we have fewer registers. When you have lots of registers, we tend to use register reference architecture. In modern microprocessor, in the early 8085, 8086 microprocessors, we only have a few registers, right? That's why they mostly use register to memory reference architecture. But the modern i3, i5 type of processor, you have tons and tons of registers. So they tend to typically follow the register to register reference architecture, right? So the older general register based CPUs followed this. The more modern ones follow this, okay? We'll see the pros and cons of both of them as we understand them in a lot more detail, right? So let's look at the register to memory reference architecture here, right? So I just showed you an example. So this is the block diagram. Look at this. Here I have something called as a register file. So register file is nothing but a collection of registers. Here I have registers from R0 to Rn. So I have n plus 1 registers in the CPU here, right? These registers, again, the ALU can pick any of these registers. So let's call this, instead of calling it n, let's call it n minus 1. So the register can pick any of these n registers as one of its operands. It will pick this as the first operand, right? And the second operand, it will pick from the main memory. And whatever is the resultant, it will end up storing it in the first operand itself. Let's look at an example. Look at this. Imagine I have an instruction like this. Add. This is the register R0 and this is the memory location. So what happens now? It takes whatever value is stored in register R0. It adds the memory value that is there in 2080. This resultant, it will store in R0. This resultant of the sum, it will store it in R0, right? So this is your first operand is your register. Your second operand is the memory address, and the resultant is stored. Resultant of this arithmetic operation add is stored in the register itself. This, again, look at this. That's why this line is two-way, because whatever the ALU computes as the output of the addition, it will store it back to your register file, to one of the registers that we have used as part of the instruction, right? This is called as two address instruction. Why is it called two address instruction? Because I have two addresses. The first address is the address of a register. The second address is the address of a memory location. So in this case, I have addresses of both the operands. One obviously being a register address. The second is your basically is your memory address. Right? That's how it works. Okay. So this is called the two address format. Now here, if you try to break this down into fetch and execute cycle, it's very simple. In the fetch cycle, I'll actually read the opcode. Look at this. I'll read the opcode and I'll read the operands. I'll read both the operands. I'll read both these operands and the opcode from memory. Now, when I execute, this is what my fetch cycle will constitute of. My execute cycle, first I'll interpret this. I'll interpret this as add, which means I have to perform addition. I know if I'm performing addition, this is my first register. Okay. So then I'll fetch whatever, because this is a memory location, I'll have to fetch this from memory location. So I actually fetch it from memory and place it as the input to the ALU. That's the second step. Then I'll perform the actual arithmetic operation of addition. So add R0 plus whatever is there in the memory location 2080. Perform this addition and store the resultant in R0 itself. This is how the execute cycle works in a register to memory reference architecture, which is one of the general register CPUs. Again, this is very good when you have fewer, remember, when you have fewer registers. When you have fewer registers, this is good because one of your operands is actually coming from the main memory. You don't have to keep all the operands in your register file because you may not have many registers. If you have fewer registers, instead of placing all of your operands in the register file itself or in the registers, you have one of them in the registers, the other in the main memory. Okay, so when you have fewer registers, this architecture works very well. Very simple concept if you think about it. Now let's look at a very simple example on how everything works. Okay, so imagine I have this here. A, B, C, D and X are memory locations. Okay, my first instruction is move from A to R0. So whatever is there in memory location A, I'm copying into register 0. Then add R0 to B. So what is happening here? From A is now copied to R0. Now this addition, basically what does it do? Whatever is there in R0 and whatever is there in B, it sums up both of them and stores it in R0. So what happens to R0 now? Now my R0 consists of A plus B. Right? So this whole resultant is in my register 0. Next I'm using another register R1. So R1 will now consist of my C. Right? From address C, whatever value is there, I'm moving it to R1. Now add R1 comma D. So what happens here? R1 is whatever is there in R1. What is there in R1? C is there in R1 plus D. Right? So C plus D is in R1. Now I'm saying multiply R0 R1. Look at this. Here I have both registers. Look at this. This operation or this instruction here. This instruction, one of these values is in register. The other is also in register. Okay. So this is actually register reference architecture. This type of instructions will be in register reference architecture. If this is not allowed, then what you have to do, suppose this is not allowed, then what can you do? You move your, in such a case, what do you do? If this is not allowed by your microprocessor, then what do? You basically say move one of these resultants. Let's say move your D to a temporary location. Okay, so move TD basically means instead of writing it as D, the resultant is in R1, right? Not in D, sorry. The resultant is in R1. So you say whatever is the resultant in R1, store it in a temporary location like T. If this is not allowed, we can solve it using multiple steps. Now what I'll do here, look at this. Now what I'll do here is this. Now instead of, look at this. This is register reference. But if this is not allowed, if only, again, lot of microprocessors, modern microprocessors allow both register memory and register reference architectures. Sometimes both of them are allowed. Here we are separating them. That doesn't mean that a microprocessor is either this or this. It could use, for some instructions, it could use this type of architecture. For some instructions, it could use this type of architecture. Imagine if this is not allowed, then what do? You store whatever is in your R1. What is in R1? C plus D. You store it in a temporary memory location called T. Then you compute this mul. Right? Now what do I want? From R0. What does my R0 contain? My R0 contains A plus B, comma T. Now what is in T? C plus D is in T. So whatever is there A plus B, that is multiplied with C plus D and it is stored in R0. Now here if you look at this command or this instruction here, this says whatever is there in R0, store it back to your memory location. Okay, this is also register memory because one of them is a register, the other is a memory. Just the order is slightly different. That's it. Okay. So this is one way. Again, if your lot of modern microprocessors allow you to have both register memory and register. You can do both of them, right? So again, this instruction is a register architecture instruction. If this is not allowed, we can always replace it only with register memory or register to memory reference architecture based instructions also. Okay, so now let's solve a couple of simple problems, right? So imagine if I have a microprocessor. This is a good problem. Imagine if I have a microprocessor that supports 2 address instructions, 1 address instruction, and also 0 address instructions, right? So it supports 2 address, 1 address, and 0 address instructions. Okay, here we always assume that expanding opcode is being done. Okay, so let's always assume that we can do expanding opcode. Okay, that's something that is implicitly assumed. I have 20-bit instructions, so my instruction here is 20 bits. Cool. So my whole instruction is 20-bit. My memory is 512 word. So what is 512? 2 power 9. So which means my memory location, look at this, my memory location requires 9 bits. So 9 bits for my memory location, where my operand 2 will be there. First, let's look at it from the perspective of 2 address instructions, right? I have two address instructions. Okay, I have two address instructions here. Okay, cool. So since I have two address instructions, look at this, I have two address instructions. So if I allocate 2 bits, let's assume I allocate 2 bits for opcode, then what happens now? Let's look at this, right? If I allocate 2 bits for this, because I have two address instructions, what happens? If I say, if I have 2 bits, right, I can use 0, 0. What are the 4 possible values? 0, 0, 0, 1, 1, 0, 1, 1. If two of these values, if I have 2 of these values, I'll interpret this opcode to be a 2 address opcode. I'll interpret it to be an opcode of a 2 address instruction, right? If I do that, right? So imagine if I just take 1 bit for this opcode, then there is a problem. Look at this, instead of 2 bits, if I just took only 1 bit, imagine if I took only 1 bit here, 1 bit can take 2 addresses, right? 1 bit can take 2 addresses. Now 1 bit can only have, or 1 bit can take 2 values. Now if this most significant bit here, this is my most significant bit, right? If my most significant bit is 0 or 1, then if it represents a 2 address, remember, if it represents a 2 address instruction, then I can't differentiate between 2 address instructions and 1 address instruction. So it can't be 1 bit. It has to be at least 2 bits. It has to be at least 2 bits. If it is 2 bits, then what happens? I have 4 distinct values. I have 4 distinct values, right? Then I have 4 distinct values. Two of these values will be interpreted as 2 address instruction, 2 address instruction opcodes. The rest can be used for 1 address or 0 address, right? So very simple concept here, right? So let's assume, so how would it work internally? The control unit will first read the 2 bits. If the 2 bits are 0, 0 or 0, 1, it will interpret the rest of it as it will interpret the rest of this instruction as a 2 address instruction. So if this is 2, this is 9, we have 20-bit instructions, right? 2 plus 9 is 11, which means this will be 9. So the register space is 9 bits now. Again, this is not given to us. We arrived at it by looking at what is the minimum number of bits required for the 2 address instruction, right? So since there are 2 distinct 2 address instructions, these 2 values will basically correspond to the 2 address instructions, which means I'm left with 2 more options here, because there are a total of 4 possibilities, right? 2 options. For these 2 options, I can either use it for 1 address instructions or 0 address instructions. Okay. So now if I remove these 2 options, how many options am I left with? In this place, I'm left with 2 options, because out of the 4, 2 are taken by the 2 address instruction. So how many opcodes are, or how many possibilities am I left with for 1 address and 0 address? First, let's look at it from the perspective of 1 address, right? So what will 1 address look like? Look at this. Your 1 address will have, okay, so let me just erase this. This is your 2 address format, right? How will your 1 address format look like? Your 1 address format will look like this. You will have 9 bits for memory. Because you have a 512 word memory, you need 9 bits for that. The rest, everything will be your opcode. The first 2 bits can either be 10 or 11. Either of them is okay. The next 9 bits can be anything. So how many possibilities do I have for one instruction, for 1 address instructions? How many possibilities do I have here? 2 possibilities here and 2 power 9 possibilities here. 2 into 2 power 9, which is 2 power 10 possibilities here in total, right? That's the total number of possibilities that I have. And what is 2 power 10? 1024 possibilities. So I have 1024 possibilities for one address instruction, but it says I have only 151 address instructions, which means how many are left, how many possibilities are left? If I subtract 150 from 1024, I get 874, right? I am left with 874 possibilities. Now let's look at the world from the perspective of zero address instructions, right? So how would my zero address instruction look like? I have these 9 bits. This whole thing is my opcode now. This whole thing is my opcode now for zero address instruction, because we are using the expanding opcode strategy. Now in these first 11 bits, look at this, in these first 11 bits, look at this, in the first 11 bits, I am left with 874 possibilities that I can use for zero address instructions, right? I am left with 874 possibilities here, because first we have removed all the possibilities for 2 address instructions, all the possibilities for 151 address instructions. Now we have 874 possibilities here. How many possible values can I have here? Because all these can be occupied by the opcode of the zero address instruction, right? So here I have 2 power 9 possibilities. So what is the total number of possible zero address instruction? 874 into 2 power 9, right? Look at this. The complexity is increased now. In the previous videos, we have seen only 1 address instructions and 0 address instructions. Here we also have 2 address instructions. We'll also see 3 address and 4 address instructions as we go forward. Okay. So let's look at one more example here. Okay. So imagine this instruction format. Okay. So imagine that we are given an instruction format like this, where you have opcode followed by register address followed by memory address. If I have lots of registers, I might want to refer to registers also with addresses. So here it says I have 128 registers. To represent these 128 registers, I need 2 power 7. So 128 is 2 power 7, right? Which means I need 7 bits in this register address, right? Because 128 is 2 power 7. So this implies the register address field is 7 bits. Okay. Next, I have 256 mega word memory. What is 256? Let's work it out, right? What is 256 now? 256 is 2 power 8 into 2 power 20. So 2 power 28 words, right? That's what I have now. Okay, cool. 2 power 28 words is what I have for my memory. Okay, simple, cool. Now, if it is 2 power 28, 28 plus 7, something is not working. Actually, I think this should be KB, not mega. Okay, because then the problem won't work out. Sorry. So this has to be kilo words, because if it's mega words, this is 28, this is 7. 28 plus 7 is 35, but I only have 32-bit instructions, so nothing will work out, right? So there is a typo here in the question. It should have been kilo words. If it is kilo words, what happens here? This becomes 10. So this becomes 2 power 18, which means for the memory address. So the memory address will need 18 bits. The instructions are 32-bit. Look at this. The instructions are 32-bit long. Okay. So the whole instruction itself is 32-bit long. Okay, cool. Now, how many do I need for memory? I need 18 bits for memory, right? I need 18 for memory. I need 7 for, look at this, I need 7 for my register. How many are left now? 25 are occupied here. So I'm left with 7 more here for the opcodes. So it says I have n 2 address instructions. Okay, I have n 2 address instructions. So 2 address instructions will require both the register and the memory address, right? So I have n of them. Okay, cool. So if I have n of them, so then how many am I left with? So I'm left with n of, so I have n 2 address instructions. The question here is how many 1 address instructions are there? Now there are 2 ways to think about it, right? Look at this. My opcode, register address and memory address. I have n 2 address instructions. Okay. So how many 2 address instructions can I have? 2 power 7 here. Okay, I can have 2 power 7 with 7 for register and 18 for my memory address, right? Of these 2 power 7, n of them are 2 address instructions. N of them are taken. So minus n. So this is what is left in these 7 bits for me. This is what is left in these 7 bits for me. Now how many 1 address instructions can I have? So in the 1 address instruction, look at this. This part will still be there in a 1 address instruction. Only this part is freed up for me. Only this part is freed up for me, right? If you think about it. So in the 2 address instructions, n of them are taken. So 2 power 7 minus n is there. So 2 power 7 minus n possibilities are there in these 7 bits. These 7 bits, I can have any of them. I can have any of the 2 power 7 possibilities here, right? I can have any of the 2 power 7 possibilities here, right? So how many 1 address instructions can I have now? Because my opcode, look at this, my 1 address instruction will look like this, right? It will have just an opcode for 14 bits. It will have opcode for 14 bits, right? And it will have 18 bits. So it will have 18 bits for memory, right? Of these 14, look at this, of these 14, the structure that we have in 2 addresses, what is 2 power 7? 128, right? 2 power 7 is 128. So I can write this as number of 1 address instructions. How do I compute them? Of these 7 bits, I can have 2 power 7 possibilities. Of the 2 power 7, n have been taken by your 2 address instructions. So how many are left for 1 address instructions? 2 power 7 minus n. So after the 2 power 7 minus n, these can be anything, because I'm just doing the expanding opcode strategy here. So 2 power 7 minus n into 2 power 7. That's the number of 1 address instructions I can have. Very simple. Now let's look at one more possibility here. If I have n 2 address instructions, m 1 address instruction, then how many 0 address instructions can I have? This is a good question. Okay, now let's look at this. Look at this. So I have n 2 address instructions. Okay, so let's go step by step. Here we have to be careful. Okay, so how many do we have here? So how many 1 address instructions are possible? 2 power n. So let's write that. So number of 1 address instructions possible are 2 power 7 minus n into 2 power 7, right? Out of these, I have to subtract m. Out of this, I have to subtract m, right? Because I have m 1 address instructions, right? Suppose if I subtract m from this, what do I get? So what is this number? Let's understand this, right? So we have 18, 7, 7, right? So we have 18 and let's call this as 14 just for simplicity, right? In these 14 possibilities, look at this. In these 14 possibilities, these are the number of possibilities that I have for 0 address instruction. In these 18 positions, I can have anything. So 2 power 18, right? Till now, what is this number? Look at this. Till now, we are only, look at this. This is the number of 1 address instructions, right? So we are only talking about these 14 bits now. We are not talking about the 18 bits, right? So within this is the total number. Look at this. This number here is the total number of 1 address instructions that are possible. Amongst them, there are m 1 address instructions. So you subtract m. So which means within these 14 bits, the number of possibilities that we have is this much. Within these 18 bits, I can have 2 power 18 possibilities. So the number of 0 address instructions here is this. Here there is a small catch, which is here we are assuming that the 1 address instruction has the format. Look at this. Here I've made an assumption without being explicit about it. The 1 address instruction that I've assumed is that I have the instruction opcode and a memory location. This 1 address instruction is opcode, comma memory location. That's the type that I've assumed. But I could also have 1 address instruction. This is one possibility. What if the other possibility that I have here is this? My 1 address instruction is opcode, comma my register. Not the memory, my register. Then this whole number will change. If that's the case, this whole number will change, right? This whole equation will change now. Because in such a case, what will happen? Look at this. In such a case, what will happen? Let's think about that. That's a very good twist actually. So what do we have now? So we have total of 32 bits, right? We have a total of 32 bits that we have broken up into 7, 7, 18. Now what are we saying? My 1 address instructions are opcode, comma register. It will occupy this. This whole thing is free. This whole thing is free. So my 1 address instructions will occupy this and this. That's what we are saying now, right? So within this first 7 bits, n addresses have been occupied by 2 address instructions. So how many are left here? 2 power 7 minus n. These are how many are left in this 7 bits. These 7 bits we'll use it for the register address. How many possibilities are here now? 2 power 18 possibilities. So if we have opcode, comma register format and not opcode, comma memory format, my 1 address instructions, if they're opcode, comma memory, then this answer is right. If this is opcode, comma memory address, if it is opcode, opcode, if my one address instructions are opcode comma register, that's also a one address, instruction, right? If that's the case, how many possibilities do I have? Look at this. These are the total number of one address instructions I can have. The number of total one address instructions is 2 power 7 minus n into 2 power 18. Because these 18 bits are also at my disposal. This is where I'm storing my address, because I have a register address, and registers only need 7 bits. Because I don't have a memory address, I can use these as part of the opcode. So my opcode will now be split between this and this. So I'll have part of the opcode here, and my registers here. Slightly tricky situation. But this is the total number of one address instructions that I can have. Amongst them, if m of them are taken. Look at this. Now let's compute this, right? Let's compute this. If m of them are taken, this is what I'm left with. Right? For zero address instructions, I won't even have the registers. I will not even have the registers. So this 7 bits also can be used there. So if I have this format, if I have opcode comma register format for the one address instruction, right? Then this is the possible number of zero address instructions. If what I have here is opcode comma memory, then what I have here, this is the number of zero address instructions. There is a small twist, okay? Again, you have to be very careful. What is the actual format of the one address instruction? Especially given that we are told that there are 128 registers, which means there are a fixed number of bits that we assign for registers now. Fixed number of bits that we assign for memory. So we have to be careful when you are computing the number of zero address instructions, because it will depend on whether my one address instructions are opcode comma memory or opcode comma register. Very good problem actually. Very, very good problem, right?